So okay, let's proceed with our question 1A, right? Okay, so now we have this schema. We have this are a 5 elements, 5 attributes, A, B, C, D. Okay, sorry, 4 attributes. And now we also given a set, FD set with A to B, C, D, and C to D. Let me check. Actually, is it recorded? Is this recording? Oh yes, yes. Okay, good. Okay, so given that this decomposition, is this decomposition dependency preserving? So for last week we learned about is this if one decomposition is lossless join or not, right? Do you guys still remember? Last week you learned about lossless. So if you forgot, can read back to last tutorial. So this week you'll be learning about dependency preserving. So is this decomposition dependency preserving? How do we check this? Well, actually, we have one algorithm for that. We can use these steps to check whether if a decomposition is dependency preserving or not. So there are 3 steps here. So first one is to project the original functional dependencies onto R1 and R2. After projection, you will obtain 2 things. The first one is the functional dependency set 1 for R1 and the functional dependency set 2 for R2. Alright, so first step is to project it. And the second step is I take this functional dependency 1 and functional dependency 2 together, and I merge them together, I union them together, and I get a new functional dependency set. You name it as U here, alright? Union, okay? So now I will check if all functional dependency in the original set can be derived from this or not. Can be derived from the newly obtained U or not. If it's yes, then it means that yes, your dependency is preserved. But if it's not, then it means that your functional dependency is not preserved. So I guess we keep this. Okay, that's a no. I'll draw this out. So right now, right, a table, R relation, is split into 2 things. It's decomposed into 2 relations, R1 and R2. So how do we obtain this? How do we obtain the functional dependency set for this one?
Projection.
Yes, correct. We'll project this and we get this. We get our new functional dependency set for this one. Same goes to this one. So obtain these 2 now. After we obtain these 2 together, we'll union them together, alright? We union them together. And we'll get this one. Union, okay? You just take this, and we union them together. So now, we have this one. So of course, from this one we have like a whole list of a new functional dependencies, right? Okay. So what we have now, of course, we have a functional dependency is we'll check if all functional dependency set in this original set can be derived from here or not. Alright, got it? So the purpose, okay, so from the name suggests dependency preserving, it means that after you decompose, is it everything here is still derivable from what you decompose? So that's what dependency preserving means. Okay? Is the data preserving is a function dependency, the relationship is it still preserved after you decompose? So that's what dependency preserving means. Okay? So that's like a visualization of how we can check this decomposition, whether it's dependency preserving or not. So now we know that we have this algorithm. We'll put a cheat sheet here so that we can refer to this. Okay, so let's get started. What's the first step? Now we have this decomposition, R1 and R2. What's the first step? What's the first step? What's the first step? Project. Yes, correct. It's here. Project. Yes, you got it. Project. So now we have this. We have this projected. We have this one and this one. And what's the second step? Yeah, union, correct. We are halfway there. And now the third step is, what was the third step? What's the third step? You need to check if all the function dependency in this set can be derived from union set or not. So it means that, can we derive A to this thing, A to B, C, D, and C to D from this? So how can we do that? So we just take this, we have to check if this thing and this thing can be derived from this thing or not. Okay? So what we need to do is, we just check if this A, we find the closure of this one, we find the closure of this A, and we realize that from this U, A can go to BD, right? A can go to C there. So A can derive B, C, and D. A can derive B, C, and D. And yes, this thing is actually identical to this thing. Okay? So it means that, yes, it can be derived from this union set, union function dependency. Got it? Really? Okay. Okay. And let's try to find this one. We find the closure of this one, and then we realize that, wait, we actually cannot derive anything. So it's an empty set. So no, wait, FD, C to D cannot be derived after we decompose. So this data is basically lost already. So it's no more it's no longer dependency preserving because this data is already lost after decompose. Alright? So the answer is this decomposition is not dependency preserving. Why? Again, because this data is no longer derivable because this is basically lost already. Alright? So it means that this union, we have lost this thing, is no longer preserved. Alright? So you got it? Got the idea? Okay? Any question? No?
For the step 3, what if the one of the functional dependency on the left side has two elements? How do we check? Do we still use the cover?
Do you still use the what?
Do we still use the cover to check?
Cover to, you mean the closure?
I mean, for one functional dependency, we have more than one
on the left side?
On the left side, how do we check if it can be derived from the union?
Oh, okay. So there are multiple ways. So the first way, you can find the canonical cover for this one. Yeah, that's the first one because canonical cover guarantees that the left hand side will always be only singleton, which means only one element. But that will be very, very time consuming. So I would suggest just when you see A and B together, right, you can just by closure. So you can just find the closure. Let's say you're mentioning you are referring that you have like A, B, C on the left side, right?
Yeah.
So you just find, let's say I have A, B going to maybe C and D, right?
Right.
On this set,
yeah.
Right? So after we union this, we will find this one. We just derive A, B. We just find the closure of this one. We'll see whether if this thing will consist of this or not. Can derive this thing or not.
Okay, so we just find all the closure for all the function dependency in the original original set, right?
You just find the closure of the left hand side in the original set. That's right, that's correct. Okay. You got a key. So we just need to find the closure of this one and we see whether if it's still derivable, if it's still able to get this one. Yes, that's correct. Yep. Any other question? No? Then?
So if there are multiple, because when you union them, so there are multiple functional dependency.
Yeah.
So as long as one of them is not dependency preserving, then the whole thing is not.
Yeah, that's right.
Okay.
So as long as one is not, then the whole thing is not, because the data is lost. And lost means it's no longer dependency preserving.
Do we need to show the procedure how we find the closure?
Okay, I'm not very sure how your exam will be like, but for my time, right, most of them are objective questions like ABC. Yeah, so but we have like until like G or something like a lot of options basically. So
You mean the MCQ got options until G?
yeah, it happens.
Your time is how long ago?
I think 1 hour or 1:30, but a lot of questions. I forgot already. It's been some time. I don't think you need to show the stats. Yeah. Okay. But you might need to show the stats because I don't know how the exam will look like. Okay, so this is our first question, 1 So, is everything okay? Know how to do this? A lot of people nodding. So, wait. Oh, no. And then I just show the answer already. Okay, so now we have another decomposition. Question is the same one. The function dependency set still remains the same. We have a new decomposition with this and this, R1 and R2. So, what's the first step again? Projection. Okay, after projection, what's that? Union. Okay, so after projection, the project, and then we union them. And for the third step, we will check, right? We'll check if each function dependency in the original set can it be derived from this union U or not? From this union function dependency set or not? Okay, so now we have this, right? So we'll check the closure. A closure is A to B to C and C to D. So A has A has B, C, and D. And yes, it fulfills the first one. And the second one, C to D. We'll check the closure of C here. C to D. Oh yes, this function dependency can be derived. Okay? Oh, can be derived too as well. So what this means, since both of the function dependency sets, all of the function dependency sets in the original sigma can be derived. So what does this mean? This means that, is it dependency preserving? Yes, that's correct. It is dependency preserving. Wait, I wrote this one already, okay? This is KD, right? Right? Any other questions before we move further? No. Okay, so we got it with our dependency preserving already. So now let's actually move on to shred F. Consider that we have this schema, A, B, C, D, E, 5 attributes, and we have a set of function dependency here. Is this relation, is it in 3 and F? How can we be sure? What algorithm should we use? Is there like, okay, there's no algorithm, but did we talk about this earlier? Which one? What's the thing that we should use when we see this question? What approach?
Algorithm 5? Algorithm 5?
No, algorithm 5 is creating 3 and F. How do we check if one is 3 and F or not?
The 3 conditions.
Yeah, we should just apply the 3 conditions. Yes. Remember the definitions that we talked earlier? We have like 3 conditions, right? So we just need to see whether all function dependency whether fits the 3 conditions or not. If all of them fits, then it is in 3 and F. So that's for checking. And for algorithm 5, it's to create a 3 and F from a function dependency set. Yeah. Okay, so this is the the rules, the definition. So we just check according to our definition here. Still remember this? Okay, so now let's find the candidate key first, because we actually don't have a candidate keys. Still remember how to find? Yes? Okay, that's good. So the candidate keys are AC, CD, and CE. Alright? So this is our candidate keys. From this, can you tell me what's the prime attributes? What should A? Yeah. A, C, D, and what's the last one? E. Yes, correct. A, C, D, and E. Okay. So let's move our 3NF definition to here. We'll put a cheat sheet here. Okay, so first, what we want to do is we want to check if every single functional dependency in this sigma fulfills the 3NF rule or not. So let's start with the first one. Okay, is this A to B, D, E, is it trivial? No. Yes, it's not. Is this A super key? Let's move the left hand side. Is it a super key? No. Why? Because when we find the closure, we will realize that wait, it's not, because it cannot derive all the attributes in relation. So this A is not a super key. And the two one is all the attributes in the right hand side prime attributes. Is it B, D, E? Is it? Oh, no. Yes, it's not. Why? Because we have in the right hand side we have B, D, and E. We have a B here, and B is not in any candidate keys. So B is not a prime attribute. Since all the 1, 2, 3, all the rules, we have not fulfilled any of the rules. Is this in 3NF? No. Wait, yeah. Yeah, the answer is not. Okay? Just like that. Checking if a relation is in 3NF or not. You just apply this rule. Okay? So let's say with the first one is indeed fulfill one of the rules already. What should we do next? Let's say if the first one is indeed already in 3NF. What should we do next?
Check the next one.
Yeah, we just check the next one because we need to check every single one to see whether it fulfills the 3NF or not. Okay. Okay, so now let's move on to. Before that, any questions?
Just one question.
Oh yeah.
The candidate key, right? Do you find all or just one symbol?
I would say find all.
Find all.
Find all.
Okay.
Yeah. Okay. So for question 2b, okay, let's find a 3NF decomposition that is both dependency preserving and lossless join. Okay, familiar? Which algorithm should we use?
5.
Algorithm 5.
Yes, correct. Algorithm 5. Why we can use algorithm 5? Because the algorithm 5 guarantees that it is a lossless join and dependency preserving at the same time. So we can just use algorithm 5 for this question. Okay, so now let's move this and we put up here. Okay, now we have a cheat sheet here, okay? So what are the steps? The first step is to find the canonical cover. I hope you guys still remember how to find that. We'll find this tree, A to E, C, D to A, and E to B, D. This is our canonical cover. And from the canonical cover, we'll create one table from each functional dependency by taking both the left-hand side and the right-hand side. What does this mean? Okay, this means that now we have 1, 2, 3. We have 3 functional dependency. So I just take this one. I just put the left-hand side and the right-hand side together, and I'll form a new relation. So this is our first relation, and this is the same thing. I just put together. We have a second relation, and we put the third one together, and now we have a third relation. So this is how the second step works. All right. And now the third one. If no relation from this tree contains a candidate key, then we'll pick any candidate key is here, and we'll create one more table with it. Okay. So, do we have any relation contains a candidate key here? Yes, right? Because AC, let's say AC, right? One of the candidate keys is AC. It's already within R2, so we don't need to create a new one for that. But let's say that we don't have this relation here. Let's say we don't have R2 here. Then we realize that none of the candidate keys actually is part of any of the relation. In that case, we'll take AC and we'll create a new one. We'll say R4AC, R4AC. Okay? So that's one sub rule here, so that if you realize that your candidate key is not part of any relation, we just create a new table with it. Okay? But since we have already, so we just don't need to create any additional table. Wait, like that. So you got it? So, what's the answer? What's the answer? This one? This one or this one? Which one? What's the decomposition? Where's the decomposition? Yeah. This is the decomposition. This is the answer. Okay. R1, R2, and R3 is the decomposition. Okay.
So we don't need to check the projection because it's already guaranteed.
Yeah, it's already guaranteed.
Okay.
So no need to check. Yes, from this algorithm, if we do it correctly, then it guarantees a 3NF, the dependency preserving, and a lossless join. Okay.
Do we need to
Let's-
find the minimal cover first?
We need to find a canonical couple first. So what's the difference between minimal cover and canonical cover?
No, can only have one and one.
Combine.
Yeah, correct. So one, the left hand side, right, or the right hand side? Left hand side, right. One is with only single element, and the second one is needs to be combined together. Right, that's the difference, right? So now let's move on to 2C. Let's consider the schema. R will be 5 attributes A, B, C, D, E, and we have a set of functional dependency sigma here. And is the decomposition in part B above in BCNF. So if you still remember, this is our decomposition. So the decomposition is R1, R2, and R3 is here. Is this in BCNF? How do we check this?
The two conditions.
Hmm?
The two conditions.
Yes, the two conditions. But okay, so if you still remember, the two conditions are for all the functional dependency in the functional dependency set. It's either non-trivial, it's either trivial, or the left hand side is a superkey. That's the rule for BCNF, right? Two rules. But for now, actually, which FD set should we actually check? Is it this one? Is it something else?
Projected.
Ah, correct. We will check the projected one. Why? What if we check this? What does this mean? It means that we are checking if this relation is in BCNF or not. It doesn't check the decomposition at all. Okay. So yes, that's correct. We'll check the BCNF using the definition, which is here. We have the cheat sheet here also to refer. So now let's just check out. We have this R1, R2, and R3. What's the step to project, right? Project, right? But do we need to project for R1? No. Why?
Maybe it's a attribute.
Yes, correct. So if you guys still remember from last tutorial, I mentioned about a very easy, very simple, but a very I would say advanced trick, which is any table with two attributes is automatically BCNF, so you don't need to check it. So in this case, the R1 is two attributes, so we don't need to check it. So it's automatically in BCNF, alright? And now, what we need to check is R2 and R3 because they are not two attributes, alright? So again, so the steps is we need to project them. So we have R2 here and R3 here. Okay. So from R2, the projected function dependency is this one, and for R3 is this one. So let's check. Let's go with R3 first, shall we? So we have this functional dependency set 3, E to B and D. Is E trivial? So remember how do we do this, right? So we need to check every single function dependency in the set, whether it is in BCNF or not. Okay, so is E a trivial? No. Okay. Is E a super key? Yes, correct. So R3 is in BCNF. Let's check with R2, A to D. Is A trivial? A to D trivial? Is A to D trivial? No. Is A to D super key? No, right? Wait, it means that both rules, this function dependency cannot fulfill both rules, right? So A to D is a violation, and therefore R2 is not in BCNF. So what does this mean? We have one violation, but the other one is not. R1 and R3 is not a violation. R2 is a violation. Is this decomposition in BCNF in the end? No, because there's one violation. As long as there's one violation, then the whole thing is a violation. Alright? So yes, this is a violation. Therefore, this decomposition is not BCNF. Oh, okay. Any questions?
Why do we check the R whether is it because we check the R whether is it in 3NF or whether it's in BCNF, right? Why do we need to check the decomposition?
Oh, the question asks us whether the decomposition is.
The question asked is the decomposition in BCNF. Why do we need to check the decomposition?
You mean like in real life you need that, right? For example, right, the decomposition can be looked in this way, so that we have like a huge table. We have a huge table, right? Then we probably the company policy or something, they want us to split this table into multiple tables. That's where the decomposition comes in. Because in tables we have like multiple attributes. Let's say we have A, B, C, D, E attributes. So now we want to split into 3 different tables. Yeah. So this one will be our first table, this one will be our second table, and this one will be our third table. We have to check whether after splitting, right, if this table is still in BCNF or not. Yeah. So that's the decomposition comes in. Okay, quick. Any questions? No? Are you sure? If no, then I have question already on. Okay. No question. Then my question is, after decomposition, right? We realize that that decomposition is not in BCNF. What are the further steps that we need to take to get a BCNF decomposition?
Find the function dependency violating BCNF.
Is it?
Decompose the
Yes, we further decompose. Yeah, we further decompose the R2 here. So after decomposition, if we're still unable to find the BCNF, we just further decompose the violated function dependency. So that's how we find it in the end. You'll definitely find one at the end, because in the end, you'll decompose it probably to 2 tables, 2 attributes in the end. And I don't think the exam will like make it like very difficult for you, like you need to decompose a lot of times. Okay, I don't think they'll do that. Okay, but to find a BCNF after decomposition is by further decomposing it, the violating function dependency. Okay, got it? So, yeah. So there's one thing that, okay, this okay, right? Is this okay? Okay, then we'll move on to another one. This is actually all the tutorial questions already. Yeah. So, but before that, you still got time. I'll do one thing that I'll have a last note for you, like things that you might miss during this tutorial. Right. So let's say we have this schema with 5 attributes, and then we again is R in 3NF. We just need to check if every single functional dependency whether it fulfills the 3NF rule or not. If it fulfills, then yes. If it's not, then it's not in 3NF. So let's take this one. A to BD is certainly not trivial. A is not a super key too, but its right hand side prime attribute or not. So we have the candidate keys. This is given. Let's say this is given. The candidate keys are A, C, C, D, and C. So the prime attributes are A, C, D, and E. So let's look at the right hand side. We know that D and E are prime attributes, but B isn't. Okay. Does this fulfill the third rule? What I mean is, we have 3 attributes in the right hand side. Is it as long as one of them is prime attribute, then we fulfill this condition, or we need all the attributes in the right hand side to be prime attributes to fulfill this condition? Oh. Who think is only one? Can you raise your hand? Who think it's all? Okay. The answer is yes, you're right. So all the attributes in right hand side must be prime attributes. In fact, this is actually the question 2a. Okay, I just use the same question. Okay. So the third rule is all the attributes in right hand side, is it prime attribute? Yeah. So I think that's all of it for today's tutorial. Okay. But before that, right, we have a last note, which is this is actually our last tutorial. I hope you guys have a really happy journey in this IT5008. And if possible, I think you can provide this student feedback exercise. You guys have this, right? Do you guys have this?
Do we have this?
Canvas.
Canvas?
Yeah. I think Canvas or email, I think they're the same. Yeah,
Okay.
that's the link. So this one is for the university. So if you guys think I'm doing please nominate me, okay?
Feedback and nominate, what's the difference?
During the feedback, they'll ask you like, is this okay? Does he teach okay? Then in the last session, they'll ask, would you like to nominate this guy?
Nominate for a certain award or something like that, is it? Teaching assistant award or something like that?
Yeah, it's like there's something like that. It's
Something
like
like
a
that.
standard certificate of recognition, something like that. But I don't think you can vote me because you're from another tutorial. So you can only vote for a tutorial. Yeah.
Cannot I can put a specific name, right?
You only have like the option of your tutor only. You only show the tutor only.
But we are all from the other tutorial.
Either way, I'm still happy to teach you guys, okay?
Do we get the slides?
Oh yeah.
Yeah, let me send it to you.
Oh,
Okay.
okay.
I have the slides.
I have the link to.
Yeah.
It's a-
What's
So.
the link? What's the link?
Oh yeah, you're not from my tutor.
I don't have, I sent it to you guys.
I sent it via my email. That's why.
I'll put my WeChat first.
Yeah. Never mind.
No, we can still put there your name, right?
No, I don't think so.
We just try it.
Okay, so another thing is,
I think
yeah.
for this one, the next one, you need to open for everyone the link.
This thing,
The next one.
this one.
Yeah.
I
I don't think you open for.
Oh my god.
Yeah.
Really?
Just try to open it up. I need your approval to get it.
These are Google Docs.
Interesting. Oh.
So then you go to the form and share.
I think so.
I think you can. No, share. I think glass button with the human characters. The next, this one.
Oh.
You need to.
This one?
Everyone with the link, yeah. Otherwise,
Oh, it's the same thing.
Yeah.
Okay. So, okay, the last note. Okay, this is actually for me myself, okay? This is not from university. So I can tell that, I think you guys can tell that I'm quite young. I'm still quite, compared with you guys, I'm still like a child, okay? So you guys have a lot of more experience in life than me. So if there's any advice that which you would like to give me, or probably to your younger self, okay, what would be it lah? So I think yeah, what words would you like to give to your younger self? Mm-hmm. This is the link. This is for me lah. Okay. Alright. And yep. And
What's
that's
the link from the nomination kind of thing from the school or?
the nomination is from the school, but this one is for me.
Okay, the other one not sent yet. I didn't receive anything.
Yes, you receive the.
I didn't receive anything to feedback
yeah.
on the TA. So
Oh, never mind. Okay, page. I think it might be in the email or the canvas.
email or canvas. Sorry.
Shit. Did that. Maybe this one is not here. Never mind. Okay, yeah, thank you guys. Yeah, that's before ending our last tutorial. Is there any questions that guys like to
We can still reach out to you via email.
Yeah, of course. Oh yeah, just can take. Yeah. No problem. Just come and take.
Did you forget?
Boy.